Are you facing difficulty in class 11 coping up with organic chemistry? Are you puzzled to see the multiple bonds, the sigma and the pi bonds? Then yes, you have logged into the correct place. This is alkenes, which is a part of hydrocarbon chapter, and we know that alkenes have the general molecular formula of CnH2n. So this is very easy. Just know the general molecular formula. Know that they are also known as olefins. Why? Because they are oil forming. They form oils. The simplest example of alkene is ethylene, or you can say ethene with a double bond. So it is C double bonded C and the 2H like this, C2H4. So this is the simplest example of alkene. Okay, so now the structure of the double bond. In the structure of the alkene, in the structure of the ethine, we can see that there are 4 carbon-hydrogen sigma bonds. These are the carbon-hydrogen sigma bonds. There is one carbon-carbon sigma bond and there is one carbon-carbon pi bond. So there are 4 carbon-hydrogen sigma bonds. There is one carbon-carbon sigma bond and there is one carbon-to-carbon pi bond in the structure of ethene or ethylene. Structure of the double bond, it's like this. These alkenes are easily attacked by reagents or compounds which are in search of electrons. Why? Because it has a pi cloud over here. Such reagents are called electrophilic reagents. That means alkenes are susceptible to electrophilic addition reaction. What is the type of reaction that takes place in alkenes? It is electrophilic addition reaction. You don't need to worry listening to all these terms because I'm going to explain the term properly to you. Electrophile means that which is having less of electron. Now your alkene system is having a pi cloud, on account of which the electrophile can get the electron density over here. So it is an unsaturated compound. You can obtain a saturated compound from a double bond. You can get a single bond, hence addition reaction. And the addition reaction can take place with the help of an electrophile. So it is an example of, or it is susceptible to electrophilic addition reactions. The presence of the weak pi bond makes the molecule unstable and more prone to electrophilic reagents. So this is the overlap. This is the orbital picture showing the sigma bonds only. So the carbon atom in CH2, double bonded CH2, is sp2 hybridized and it is having 3 sigma bonds. So it is sp2 hybridized and it is forming this sp2 sigma bond, this sp2s sigma bond, sp2s sigma bond, because 1s orbital of hydrogen is overlapping with the head-on manner with the sp2 hybrid orbital of the carbon in ethene. So this is the sigma bond. What about the pi bond? The pi bond is actually undergoing lateral overlap. So this is the pi bond, the lateral overlap that you are seeing. And if this is the sigma plane, the pi bond is above and below the plane, looks like a banana, and so it is known as a banana bond. The pi cloud is symmetrically arranged above and below the sigma plane. Now this C double bond C bond length is 134 picometer. It's of a double bond, CC double bond. Now, here we can see C2H4, it is ethene, and next homologs having 1 carbon atom extra, it is propene, butene. Now, bute system can have 2 possibilities of the double bond, and these are the 2, I will say, isomers, and they are what? Bute 1-in and bute 2-in. They are position isomers. Why they are position isomers? Because they differ only in the position of the double bond, so they are position isomers. The double bond is between 1 and 2 in but1ene, and between 2 and 3 in but2ene. The number which is in the name is the lower number. If it is between 1 and 2, it is but1ene. If it is between 2 and 3, it is but2ene. Now here we can see a diene system. So now it is butane. So you actually have butane if it is without any pi bond, butene if it is with a pi bond, but it is a diene. So here it will be butadiene system. Now you have to give the numbers. Okay, numbers will be 1, 2, 3, 4. So double bond is between 1 and 2. So the position is 1. Between 3 and 4. So the position is 3. So buta. 1, 3 diene. As if in a butane system, the diene, that means the ene is present as a substituent. So buta 1, 3 diene. Now here total number of carbon atom 1, 2, 3 and 4, but the main chain contains 3, branching is 1. So branching is present in 2 positions. So it is 2-methyl propene, yeah, prop1ene. Over here 1, 2, 3, 4, 3 position there is methyl, 3-methyl butene. Write the IUPAC names of the following. Here again you have to search for the longest carbon chain containing the functional group, that is the double bond. You also need to keep in mind the lowest locant rule. So obviously the numbering should begin in order to give the large number of carbon atoms, long chain. Following this, the solutions are here. You can check with your try. These are solved examples, and calculating how many sigma and pi bonds exist in those structure. You need to take the help of the complete structure and then only find out. Isomerism, again, it exists as structural as well as geometrical isomer. Structural isomer, we can see here what is happening, that here it can be written suppose a butene system C4H8, how many structures it can have with the pi bond, the double bond between 1 and 2, the double bond between 2 and 3, so but1ene and but2ene are the 2, and then I can keep only 3 carbon atoms in a chain, and I can change the position of the 4th carbon atom and give the double bond in any of the position. You will get only one structure. Now, there are 2 types of isomers you can see here. One is chain isomer and the other is position isomer. Remember that the isomerism that exists between the straight chain and the branching is the chain isomer. So with 1, 3 is a chain isomer. With 2, again 3 is a chain isomer. They are chain isomers. But what is the position isomer? The chain, the basic structure, the number of carbon atom in the straight chain remaining same. Only the position of the double bond changes. That occurs in 1 and 2. So 1 and 2 is an example of position isomer. It is an example of position isomer. Now again, write the structure and IUPAC name of C5H10. So it is CnH2n. So we know it is an alkene. So first you write 5 carbon atoms in a straight chain, giving the double bond between 1 and 2. Change the position of the double bond, make it 2 and 3. And it remains the same. If you give between 3 and 4, it is same as 2 and 3. Now decrease 1 carbon atom and keep 1, 2, 3, 4. 4 carbon atoms in a straight line, and then give CH3 as a branching, and then you can change the position of the double bond. You can keep it in 2 and 3, you can keep it in 1 and 2, and then you can write another one where you can change the position of the methyl, and so you can do it 1, 2, 3, 4. These are the possible structures. So you have to try it on your own to find the as many possible isomers can exist. Okay, so geometrical isomerism exists between this type of alkene only. So I will say CAB double bond CAB type type alkenes or CXY double bond CXY type alkenes, where if X and Y remains on the same side, then it is a cis isomer, and if it remains in diagonally opposite side, then it is a trans isomer. So when you draw the geometrical isomers, you get this type: cis-butyne, trans-butyne. It's a butene system. 1, 2, 3, 4. 1, 2, 3, 4. It's a but system. So if you have same or similar groups on one side, it is cis. And if you have same or similar groups on opposite side, it is trans. The trans isomer always is less polar or non-polar than the cis. Cis form of the alkene is found to be more polar than the trans form, because there exists a dipole moment in the cis isomer, whereas on account of the structure of the trans isomer, the dipole moment cancels out and gives you almost a zero dipole moment as the residual moment. And for that reason, the trans form is a non-polar form. And dipole moment or bond moment is a vector quantity. So if two opposite vectors are like this, equal in magnitude, the resultant of the dipole moment has to be zero. So it is like this. In case of solids, it is observed that the trans isomer has higher melting point than the cis form. Why? Because they are more closely packed in the lattice structure. So for that reason, why are they more closely packed in the lattice structure? Due to greater symmetry. It is having greater symmetry and so better close packing. And so in the solid state, its melting point is high. Draw the cis-trans isomers of the following. Here we can see it is again AB type, and you can draw the cis-trans isomer. Here again it is A and B type, so you can form the cis-trans isomers. So you may be given MCQ where you have to search which of the following exist as cis and trans. So you have to see whether it is identical or bonds present or not. Which of the following isomerism, compounds will show cis-trans isomerism? See, the answer is 3 and 4. Why? Because here it is CAA double bond CBB type. So it's not possible. Here again it is CAA double bond CAB type. Or I can say CD, not AB, CD type. So it's not possible. But here it is CAB double bond CA-B type. That means this is alkyl group, this is also alkyl group. So it is similar though not same. So this can show cis-trans isomerism. This needs to be CH. If it is CH, then it is CAB double bond CAB type, and it's given wrong over here. This needs to be corrected. So these are the two things that show, this type of isomerism, cis-trans. So that's all for this session. We will clear out more doubts in the next session with the reactions of alkenes. Till then, bye all of you.